Okay, welcome to thermodynamics. End of chapter 3 is talking about sort of the effects of all this stuff that we're going to be studying. And I haven't really studied it yet, but we're going to. The last slide we were talking about with the petroleum demand and whatnot. Actually, was that, I think last slide. Yeah, we were somewhere in there. And by the way, for this energy thing, we got 3 categories going here. That's climate change, it's environmental, energy security, is sort of a political issue, oil production itself, how much does it cost? There is something called the triple bottom line in business, in everything. Nike shoes. Now we're talking energy here, but just, you know, okay, is it better for the world if you, so the economic things, we know how to measure that. That's called sustainability. It comes down to sustainability. These are 3, you have to have 3 kinds of sustainability to be totally sustainable. And one is economic. And we've known how to do that for a long time because it's, are you bankrupt or not? Are you making money or losing money? If you're losing money, is that sustainable? No. Probably not. What about the environment? So, you know, if you're doing something like in Los Angeles, I remember before they had emission controls, going to my great aunt's house in the early 1960s to stay and watching the sun come up. I thought it was a moonrise. Turned out I was staring straight at the sun in the morning coming up through the fog, the haze and all that. Is that sustainable? If they hadn't changed, there's like 3 times as many people there now. If it was 3 times worse, you know, what is that? Is it really sustainable to do that? I'd say no. So, you know, killing off all the fish, is it okay if we kill off all the fish with acid? Well, yeah, sure, let's just kill off all the fish, you know, that'll be great, but then there's no fish to eat, so what do? You go do something else. Lebanon was named for cedar trees, but there's precious few cedar trees there. There are a few cedar trees there somewhere, but that used to be a forest. The Fertile Crescent is a desert now. It was like, you know, Iran, Iraq. That used to be called the Fertile Crescent. That's where, you know, agriculture started. But now it's just sort of dry wasteland. And that not necessarily because of people, but you know, it's environmental. If you're making the environment worse, then that's not sustainable. So can you do something? And you know, these days the hot topic in environmental things is climate change. But pollution, or whether it's water pollution, air pollution, that's an issue. Anyone know about the Pacific Gyre? Know what I'm talking about?
All the garbage altogether in the water?
Everything that floats in the ocean, it's like someone described a toilet that doesn't flush. So the plastic, basically plastic and tennis shoes that float and whatever else that have fallen off of ships or washed down, they go into, you know, the ocean currents, and then there's this one place where the ocean currents circulate. In the middle, it's kind of stable, not moving much, and right there, it's just looks like a huge garbage dump. And fish and birds look at something that's nice. Oh, that looks like bright, shiny food, and they'll eat a piece of it. And then, you know, they find the birds in the area and the fish, the dead things that wash up on whatever shores happen to be in that vicinity all have like plastic in their stomach. It's not good. That's actually, there are people trying to figure out what you do about that. I mean, it's so big that you can't just take a ship and go out there for a week and scoop it all up. And then what do you do with it then anyway? But so for environmental sustainability, you want to be self-sufficient and make the environment better, not worse, to be sustainable. And the third thing, so there's economics, there's environments, and then there's people. Would it be better if, is it sustainable? Let's see, maybe in places in China, they've been using like child labor or prison. You know, I don't know the details on that stuff, but there have been issues with the companies that stitching soccer balls using 5-year-olds, and by the time they're 10 years old, they can't see because they've been looking at things that are too, they've been pushing. You can basically make them crippled by the time they're 15 years old. Is that a sustainable thing to do to your? So that's what the political. There's about people. There's about environment, and right now this is the only thing that the money really addresses. You can measure this. Some of these things are harder to measure because they aren't part of the money. But one of the things for the CO2, that there's renewable energy credits that is trying to make the carbon dioxide and the greenhouse gas monetized so that you can measure it and you can compare it and you can trade back and forth to make it better. So a renewable energy credit in Europe, I think it's $30, and in here it used to be like $6. If you can avoid making a ton of CO2, literally 1 metric ton, 1,000 kilograms, by using a solar panels, instead of burning coal, if you can make as many kilowatt hours as a coal-fired power plant or natural gas, whatever the measurement is, that means maybe it's 1 less ton of CO2 generated by coal. The coal plant, you can help pay for the fact that the renewable energy costs more by giving them a renewable energy credit for every avoided ton of CO2, and then they can sell that to a power plant that has a limit. If you then limit how much CO2 they can put out, they can put out more than their limit if they can buy this credit, and it helps fund, because every renewable ton or every renewable energy that avoids a ton of new CO2 is coal that wasn't burned, for example. So that's how you can make this into the economic system and start measuring it, and then they've done that for sulfur dioxide for the acid rain. That's how they solved acid rain, actually. It's called a cap and trade. You make a limit and then let highly efficient producers be able to give them incentive to be even more efficient, and then sell to people that it's not economic for them to do that. So anyway, sustainability in general is always going to have sort of these 3 parts, and the only one we really measure is the money. Trying to get environmental, and then the whole political, are people's lives better because you were there? It doesn't have to be about child labor. It could be, what if you go into West Virginia and you carve the top off of a mountain and you displace 3 towns, and now those people that had a good life, hunting, fishing, and off the grid, whatever, suddenly they end up in a lower standard of living because you showed up with your big shovels. That's not, you can't keep doing that, just making people's standards of living drop. So how do you address that? And how do you measure that? You can measure it with income, but that maybe doesn't tell the whole story. But anyway, sustainability is people, environment, and money. So speaking of the whole climate change thing, it's not just about, yes?
On the last page, you mentioned before everything, the triple bottom line was that.
That's it. The triple bottom line is, it's not just about, are you making money or not? Are you also improving or not wrecking the environment? And the third one is, are the people working for you getting better off or worse off?
Okay.
Or are the people in your community better off or worse off because your plant's there? That sort of thing. That's the triple bottom line. And that's becoming more common in annual reports. There are companies, a lot of companies, that are addressing the triple bottom line, because that's what sustainability has to deal with, all 3, and it's about sustainability. Carbon dioxide isn't the only greenhouse gas. Actually, one of the worst greenhouse gases is sulfur hexafluoride, which is used in like high voltage switches for the distribution system. It's like thousands of times worse than CO2 for, I'm not sure why, but it is. There's other, methane is like 24 times worse than CO2 for the long-term effect. And so that comes up with the greenhouse gas potential, GHG potential. CO2 has a potential of 1. These other things have other potentials. Some refrigerants have a potential of 1,000. Others have, actually you can use CO2 as a refrigerant. It's just hard to do because of the pressures involved. But, and some have greenhouse gas potential of 0, like air, I think, in general would. But the Intergovernmental Panel on Climate Change puts out the reports, and they also document they determine what the number is you're going to use for greenhouse gas potential of a particular thing. It's not a UN body, it's not a particular country, it is truly an intergovernmental panel. Air pollution is a different topic. But we've been successful in, especially if you go down to LA, everywhere but maybe Long Beach Harbor, and when there's not forest fire going in the San Gabriel Mountains, the air is relatively clear, maybe not clean. In fact, I have a friend that lives down there, and he got a natural gas powered Honda because it burns. You can get a little sticker that says you can use the high occupancy, fast lanes, with that, and it turns out that the specs on the exhaust from that are such that the air is cleaner coming out the exhaust pipe than it is going in. There's less nitrous oxide. So in theory, the more he drives his car, that'll clean the air.
It's acting like a filter.
Yeah, it's basically filtering it. That doesn't mean that there's more oxygen. He's consuming the oxygen, but he's reducing the carbon monoxide, reducing the nitrous oxides, because the output of his exhaust is cleaner than the standard air in the basin. Even though it's clear, it might be relatively clear, it still has all the cars and people and everything going on there. So, yeah, one way you can solve the air pollution problem is drive around in a natural gas fueled Honda. Apparently. That's not intuitive. So the question is how much? Oh, did we already do this one? We already did that one. Oh, I think we already did that one. Yeah, actually what comes down to, it's not that oil is going to go away. It's that right now it was higher here and then it's less expensive. And frankly, it's a whole lot cheaper here than it is in Europe. Anyone have experience with European fuel prices? $400 a liter. Something like that, yeah, well. And it's not that the fuel costs more, it's taxed more highly, and it's sold by the liter instead of the gallon, and it's about 4 times as much.
Yeah, South America too, it's liter.
South America?
Very expensive.
It's mostly about taxes. The fuel itself doesn't cost any more to buy a barrel from the producer to refine. The reason that taxes are higher is because Europe is more dependent on fuel, so they want people to use less. So they made the political decision to increase the price. And that's also had an interesting result. You don't find a lot of Ford F-250 jacked up pickup trucks in Italy, for example, or Poland, or France. The gas guzzling things don't happen. And if you want to buy a car that gets 50 miles to the gallon, it's probably not going to be a Chevrolet. It could be if it was a Chevy, Cruise diesel. And Hondas, which they make some in the US, but again, Japan's probably even higher prices. They're even more dependent. But the European industry is responding to customer demands for fuel economy because their prices are, fuel prices are higher, so the demand is higher, and they're eating our lunch. You can't hardly sell a Chevrolet in Europe, for example. And even these days, the Dodge, okay, you couldn't sell like a Dodge, well, you could probably sell a Dodge Viper to people that don't really care there, but your standard Dodge doesn't sell there. But now we have a Dodge Dart. Anyone know the origin of the Dodge Dart that's all swoopy?
Wasn't it because Fiat bought them out?
Fiat bought them out. It's an Alfa Romeo that's been like rebadged. I mean, they changed a little bit, but it's based on an Alfa Romeo, and it's probably a whole lot more efficient than it was when it was just a Dodge Dart. So so how did I get off on this? Is not a thermodynamics, is it? The thing I want to point is there's the price of energy is not likely to go. We're going to go down and up and down and up. And the trend is up, and that means there's more energy or more jobs for people that understand energy, for conservation, or for extracting, you know, or for renewables, all of those things. It just seems like there's going to be more money in that, and the prices go up, and there's going to be more development. That's, you know, an expanding development thing. So that's you guys. That's why you're here, is thermodynamics. So acid rain, I already talked about that, but let's talk about this. Talk about a footprint. You say a carbon dioxide footprint, or how much does something create? If it wasn't there, how much less stuff would be? So in this problem, we've got a car that's driving 12,000 miles per year, and they did the numbers for it. If we could back this up. By the way, in Europe, because climate change is an interest, they'll tell you, they don't tell you miles per gallon. It's the same concept, though. It's kilometers, liters per kilometer, liters per 100 kilometers. So a 3-liter car isn't how big the engine is. It means 3 liters of gasoline or diesel fuel will take you 100 kilometers, which is like 65 miles or something. Which that would be like, you know, 90 miles per gallon or something. If, you know, that's a 3-liter car is like a goal. Nobody's really out. They don't think there are very many people doing that. They're more like 4 or 5 liters. But they'll actually see, you know, liters per 100 kilometers. They'll also have another measure, and that's CO2 per mile, which is actually the same thing. Because if you burn a fuel, or CO2 grams per kilometer, it's really, if you burn the fuel, you're going to generate a certain amount of CO2. It's just how it's going to happen. So they're really a version of the same thing. But they actually sell them that way. So this one gives us kilograms of NOx for 12,000 miles. If you develop that into there, you can say how many grams per mile. We also have, so this is a car, and we have a house of 2 cars that's burning this much natural gas for heating and this many kilowatt hours, and we want to figure out how much nitrous oxide all of that generates for that household. This is basically a conversion, kind of. It's sort of just like the stuff we've been doing. So with the car, we got the car. It's I already know the number, so I'm just going to put it over here, and it's 11 kilograms of NOx per year. Again, like the NOx, it's not an it's nitrous oxide, NO1, NO2, NO3. We've got the house at 4.3 grams NOx per therm. And where's this coming from? It's the burning it in a chamber. Some portion of the chamber, the flame's hot enough to cause the nitrogen to come apart, and then it starts sucking up oxygen, becomes NOx. And we have 1,200 therms per year. So I don't know, 4 times 1,200 divided by 1,000, 1.2 times 4.3 in kilograms. Anyone have happy fingers on that one? .3 grams times 1,200 therms, but that gets grams, we want kilograms, so it's really 4.3 times 1.2. Do we have a number on this one yet?
4.5.
Yeah, okay. 4.996.
4.956.
We'll go with the 96, but we'll just round it to 5 probably. And then 9,000 times 7.3 grams, we get the 1,000 in there, so it's 9 times 7.3. 9 times 7, 63, 65, and
65 pounds.
so
For the house heating, are we doing 4.3 times 1.2?
yes,
Okay.
and that's because it's 4.3 grams, and times 1,200 would get us 4,960 grams, but we had kilograms elsewhere, so we're
I got 5.16.
5.16?
Yeah.
I also got the same answer.
Oh, right, well, perfect, we'll call it. What we'll do is, everything else is going to be pretty much, we'll call that 5, approximately 5. And this one's going to be about 66, because we don't have that much precision in the automotive one. But you know, one of the reasons I'm running through this is just exactly how much, if you wanted to reduce your footprint, your effect, you want to be more, you know, car isn't the worst thing. But you could get one, you know, the natural gas Honda, and that would reduce that. The heating of your home, if that's true, is relatively minimal. Generating electricity ends up, if you're using that much electricity, that ends up being 3 times as bad as driving a car around. And that's not what you'd think. Oh, you know, I've got all these numbers for my car, and I'm looking for a car that has, you know, 3% better, you know, NOx emissions because that's so important to me, and you blow this off, that means you're totally blowing off what really matters. So if you really want to reduce your nitrous oxide footprint, maybe what you should do is buy some LED lights or something, you know, and not worry about spend the money, the extra money on the car, reduce your electricity use, or, you know, insulate if you got using electric water heater. Put some insulation around it, things like that. Yes?
Is 9,000 kilowatt hours per year pretty standard for a normal house? Or
I should know the answer to that. There's ways to find out, and I don't know You know, I have that information for myself somewhere, but I didn't pay attention to it. So I think, you know, let's think about 12 months, 10, 12, I don't know.
Backtrack from dollars and cents.
Yeah, exactly. That's you know, a lot of this stuff is tracked that way.
Yeah.
If you know that there's a certain tax or certain cost per whatever, and you know what the dollar is, you divide into that. I actually did a review for the greenhouse gas effect for the footprint of. By the way, this college is relatively low. Even though we don't really do as much as we could, but between what the facilities department has done, this college footprint per student, per credit hour, per full-time equivalent student, basically take all the credits and divide by 15 and say that's a full-time equivalent student, and you divide that in relatively low, and they report on it.
That's probably pretty close. I just quickly did what my apartment was last year. It would have been about 6,000 kilowatt hours a year.
For an
So
apartment.
For a house, probably, yeah, mine's probably
Yeah,
decent.
so that's in the ballpark. I did, talking about dollar-wise, I wanted to figure out how much fuel. It turns out there's numbers for that, and you can get. It's pretty close. When I did it a few years back, 2009, I guess it was. The average cost of an airplane ticket worked out to close. It varied a bit, but it averaged pretty nicely to like 15 cents a mile, an air mile. And you could figure out there's so many passenger miles they would report. You have a passenger on it, 77 passengers on a plane, and it went 323 miles. They report that stuff, Air Transport Association, and they also report how much fuel went into the aviation sector. And you can backtrack that and how much fuel per seat mile, whatever. And it worked out that if you were getting what did it work out to? Something like 44 seat miles per gallon of aviation fuel. So if you had a 15 mile per, if you had a car that's getting 15 miles per gallon, you're driving your, Suburban or something. Wow, that's like a major energy hog. But if you're going 6 people to Disneyland, it probably saved energy to take the Suburban than to fly everybody down there. Because you got, instead of 15 miles per gallon, these seat miles, you'd have 5 times, it would be like 75 seat miles per gallon. So, anyway. Meanwhile, back at the ranch, 27 plus 60, so that's what, 88. That's like 93 kilograms per year would be the total nitrous oxides put out by 2 cars and a house, heating a house, and then electricity for it. And that sounds like it's in the ballparks. As they say, your mileage may vary. So, any other questions? That gets us back on schedule then, because we're going to start talking thermodynamics. I've talked some of this stuff, but Chapter 4 is where we really start talking about properties, and that's where we should really start digging into the topic itself, now that we're ready for all that. So most of what we're talking about a pure substance. If you have a refrigeration unit, it doesn't have a whole soup of stuff in there. It tends to be just like R134 refrigerant. Most of the time, that's what it is. That's a particular molecule, and you can predict the properties of it. Everything there will turn into liquid at a given pressure and temperature, and it all will liquefy, and it'll all, at a certain temperature and pressure, it all vaporizes. So water, CO2, CH4, if you put these all together and you cooled it down, this would precipitate first as a liquid, and then you'd have a different concentration of these. And then you cool it down some more, and that one would precipitate out next, and then it's more, and the composition would change with temperature and pressure, and that would be not a pure substance. But if you only have one of these things, the concentration always stays the same. So that's sort of what that's about. Oxygen, hydrogen, helium, nitrogen, those are all pure. We actually treat air like a pure substance because both of these, if we don't go all the way down to the temperature at which probably nitrogen might precipitate out first, like turn to liquid. I don't know how nitrogen and oxygen compare, but one's going to change. If we don't go down there, they're both going to act like an ideal gas. And we can just, so when we talk about air, that's not a pure substance, but we can, for ideal gas, as long as it stays in the gas phase, it acts like one thing, the ideal gas law. Or that's what I'm talking about with air. So most thing about the pure substance, we can either talk about that or we can blend them, but we only blend them if the composition doesn't change, and we're not doing phase change. Because water and CO2 are going to have different boiling points. There's 3 phases to any substance. Fluid, we're basically talking fluids. Fluid is something that flows. It can be a gas or it can be a liquid. Liquid, things are in motion, and they're going fast enough that the intermolecular forces don't make them stick together. If they start slowing down enough, you cool them down enough, they start sticking together, and the density doesn't change much. Because when they're sliding by with enough speed, they're kind of still as close together. When they just lock in, they just sort of lock in. That's ice. But you have to, once the ice starts forming, you get the latent heat. You're taking a little bit of energy out and slowing it, but it maintains that temperature until all the phase changes happen. Ice actually has a little less density than cold water. And we can figure out at what point you have to heat water up. This, as it goes faster, they start sliding faster and they expand a little bit. Warmer things expand, colder things contract, right? Except ice, liquid water is still, it's actually less dense than ice. That's why ice floats. And then if you make these go fast enough, there's going to be some molecules, you add heat into it, and there's some molecules that are high enough energy, kinetic energy, that they take off. They literally launch. And that's when you turn water into steam and gas. Now the molecules are flying around, more space between them. They're flying around with enough energy that when they bounce off the walls, they generate pressure. Right? And the difference in density between this and this is on the order of 1,000 times bigger. So, 1 cubic meter of air at sort of standard temperature pressure is about is 1.2 cubic meters, 20% bigger than the big white tank at the back of the room. 1 liter of water is 1 liter, which is 1,000 liters to the container. Now those are different substances. Those are just 2 of my, I tattooed those somewhere under my eyelids. That's why I remember those 2 just for points of reference. But, it's ideal gas versus liquid, and, the molecular weight air is actually heavier than water, molecularly speaking, and as an ideal gas. N2 and O2 both are heavier than C or H2O. So anyway, the gas phase has much larger spacing by a factor of 1,000, just for And it's not exactly 1,000, it depends on temperatures and pressures and everything, but at room pressure, room temperature, it's about that. So we're going to define a few things here. If you have liquid, you could have saturated liquid. That's water that is boiling, but it's still water. It's saturated. They used to think that you poured caloric into it. The heat was this stuff called caloric. And if it was so full of caloric that it couldn't hold anymore, if you poured a little bit more in, it would change phase. This is an archaic term. That was the theory. It's saturated with energy. All the energy you put into it at this point is going to result in a phase change. Or any energy you take out of a steam, as saturated steam, is going to cause it to change phase into a liquid. So that's what saturated liquid is all about. There's also saturated vapor probably in the next slide. But what happens if you have a liquid water that isn't at the boiling point? What do you call it? Yeah, well, subcooled. It's cooler than the boiling point. But it's also, you can change the boiling point with pressure. So for instance, if you have boiling water at 100 degrees C, it should be boiling. Now put it under 3 atmospheres pressure. The boiling temperature, the temperature for the saturation temperature will go up to some other temperature. But you didn't change the temperature, you just changed the pressure. So now it's compressed. It's not to its saturation point. The saturation point is temperature and pressure. At a given pressure, it'll be a certain temperature. For a certain temperature, it has to be a certain pressure to do the phase change.
So if the water is boiling, we can ask, is that saturated? Is that correct?
Water boiling is saturated mixture.
So I can get home and tell my wife, bring the water to saturated.
Yes, bring the water to saturation before you put the noodles in. Here. And then, so that's the liquid phase. The vapor phase, saturated vapor is vapor that if you cool it down at all, it's not going to be vapor anymore. It's going to turn into like a fog. Actually, clouds are saturated, beyond saturated vapor. The droplets, the vapor amongst them is saturated, and what you see is the fog is really liquid droplets that they're so small they're still like suspended, but fog is already saturated. So if you just have the vapor, that's what you call it, the vapor cloud at the boiling point. So that's the stuff that's coming off of your pot. The saturated liquid vapor mixture is what happens if you put the lid on the pot. You have the water there that's boiling, and you have the steam in there. Some steam's probably escaping. What's escaping is saturated vapor. But inside the pot is a mixture of, you've got the liquid and the vapor. And they're both saturated. They're both at that boiling, whatever the pressure is, the temperature, you can find it on a table. And then superheated vapor is what happens if you heat that vapor up some more. That's what we do in boilers, in power plants. First we change phase to vapor and then superheat it so that it's like, we'll find out about that. So that's, those are all terms that you're going to hear more of. It'll probably take a while for them to sink in. And the temperature at which the saturation happens is related to the pressure. Atmospheric pressure, if boiling water is 100 degrees C. Put it in a pressure cooker, and you can increase the pressure, and that increases the boiling temperature. People use that to cook things faster. Anyone ever hear of pressure cookers? I mean, these days,
Sure.
Yeah, the whole point is, if you increase the pressure, those pots, like they lock down and their pressures, and they have a relief valve. They have a hole where the steam comes out, and you put a thing on it that weighs a certain amount, and if you know how much it weighs and you know how big the hole is, and you've got a force per unit area, you can dial in the pressure in the pot. And then it increases a little bit, I designed a steam system for a brewery that I had, and the standard ASME requirement, I think it's less than 15 psi gauge steam system. You don't need a boiler operator permit. It's not going to explode in any fabulous way. So that's the simple thing you do for ASME code. You just stay under 15 psi and you can have steam in like a residential thing. For our system, that gave us a 240 degree steam temperature. And I tell you what, if everything wants to boil at 210 Fahrenheit and your steam's coming in at 240, it's going to condense and dump heat incredibly fast, even though the temperature difference isn't all that much. It wants to keep the surface to 240, but maybe it's 210 for the boiling temperature.
So is the reverse of this the same reason why ice on planes can sublimate into vapor without becoming a liquid?
Yes. You can have energy hit ice molecules in the grid, and give it enough individual molecule, either can melt it, but more likely, you'll see here, if the temperature here this January stays below freezing, 20 degrees during the day, ice on the street will just go away. The sun will come down and it will sublimate. The ice will go directly from solid to vapor. It probably is turning to liquid in between, but for such a short amount of time, the sun's hitting it and giving it energy, and then it basically just boils off like dry ice, which is carbon dioxide, same deal. You go to the grocery store and buy that. It just vaporizes because it doesn't have to go through the liquid. I mean, it does kind of go through the liquid phase, but there aren't enough of the molecules to like stick together, because by the time it turns to liquid phase, then it's like goes to the next phase immediately. So dry ice does the same thing, but the streets around and sidewalks around here will do that if it stays cold enough during the day with sunshine on it. Sublimation. That would be sublimation going straight from solid to vapor. Interesting thing. There's a refrigerator. There's the way that they flash cool in some places, things like lettuce. You have lettuce out in the field. You bring it in a big bin, wash the worst of the dirt off. It's all nice and wet. You put it in a wax-lined box so that the water doesn't make the box turn into pulp. You put it on a pallet, put it into a vacuum chamber that holds like 6 pallets. Close the door and suck down the pressure. You can measure the pressure, and it'll suck down to a pressure that takes it down to whatever temperature you want. The water's your refrigerant, and you're vaporizing the water on the surface of the lettuce. And if you dial in the pressure you want, you can dial in the temperature, and it'll go all the way to the core of the lettuce. The outside of the lettuce will chill down first. And as it chills down, it won't chill down anymore because that water's already down to the saturation temperature based on the pressure. But stuff in the middle of the lettuce, the pressure will kind of, it'll find its way there, and it'll suck vapor out of there. And you leave it in there long enough to get to the core. It'll much better than if you put it in a deep freeze for 5 minutes, you'd end up with a bunch of limp lettuce, right? But if you can do a vacuum thing and suck off, and based on the vacuum pressure that you're pulling off vapor, all the higher energy molecules, and it'll chill like 6 pallets of lettuce, in 3 minutes or 5, or how it depends your vacuum, how fast you can pull your vacuum. And it won't go too low. It'll limit at the pressure that's related to the saturation temperature, saturation pressure. So if you pull it down to a pressure, you'll know that water was saturated at that temperature. And I guess that will be where we stop talking today, but tomorrow your assignment is to not show up here for lecture, okay, but to check out the the job fair in the ballroom and the CERT.
So no class?
No lecture tomorrow, but we'll have lab.
Yes, in the afternoon.
And yeah, that's your assignment. Check it out, because if you're not, get information for if you're interested in. This is a job fair specifically for this department. A lot of it's going to be construction management related. But if you're interested, there'll be, like Boeing, I expect, will be there, I'm not sure. But this is, for you guys, it's good for getting internships, and it's also good for seeing what the job fair is like next year when you're looking for jobs. Yeah. Bring chapter 3 home to lab.
I have a quick question for the lab report.
Lab? Isn't this, what chapter is this, 2? It's 2. When is chapter 3 due?
Yeah, for the lab reports, mostly in white paper.
That's in the syllabus?
Did you download the syllabus?
That's probably the problem. That's probably the problem. So this one here,
Memo format.
Oh, no, I mean, it is, I just wanted to ask, like, I know it's a lab format, lab report, I was just asking, is the lab report like the memo to where you?
That's wrong.
Okay.
So there's another one that's revised?
Yes.
Are the problems, when it's correct, like when it's due, that it's incorrect?
Yeah, that's why a bunch of people hate class.
So lab